Welcome to lecture number 53 of the course on nonlinear structural analysis, theory and applications. Okay. So, in the last lecture, we have concluded our discussion on geometric nonlinear analysis. Okay. We have basically gone through how to perform second order simplified p-delta analysis that takes into account the equilibrium in the deformed configuration through the geometric stiffness matrix. Okay. And we have studied in some detail the effect p-delta effect, and we have discussed lateral load behavior. We have seen how to perform large displacement analysis, critical load analysis and so on. Okay. In this lecture, we will talk about nonlinear static analysis. In other words, we will focus on the solution strategies for nonlinear static problem. Static problem means the load is applied slowly. Okay. There is no effect of inertia and damping, right. So, we often do this in laboratory where we take structural components or systems and apply the load slowly and study the behavior of the structure. We also do the same thing numerically, okay, in a computer program. For example, pushover analysis is a very common analysis technique to understand the lateral load behavior of seismic resistant frames. Okay. So, in this topic, we will just get started, and moving forward in another couple of lectures, we will study more about this. So, today we will introduce and then talk about displacement controlled analysis. Okay. So, let us recall in lecture number 13, where I gave you an overview of solution strategies for nonlinear problem, we have discussed about what is called the load controlled analysis. Load control analysis means I apply a certain load on the structure, okay, and I iterate to achieve equilibrium so that my externally applied load is equal to, okay, of course, with some tolerance, is equal to my internal resisting force, right. And how we do that in a computer program? Okay. If I show it schematically, let us say this is my capital R, the force vector, and this is my little r, the displacement vector at the structure level. Okay. And if you recall, I use capital R to denote both internal as well as external force vector. So, the moment I put superscript E, it means external. When I put superscript I, it means internal, so that I can plot the two on the same vertical axis, capital R. Okay. So, in a load control analysis, what we do, let us say that at this point, the structure is in equilibrium. This is my nth load step. So, the displacement is this point and the resisting force is Rin, which is in equilibrium with the external force vector R superscript En. Okay. And this is actual force versus displacement response of the structure, right. Now, note that this typically little r and capital R are both vector of n degree of freedom cross unity, right. So, I cannot show it in an n dimensional space. I am just showing it, this is like 1D, this is like 1D, but putting a bold symbol here to remind us that these are vectors. Okay. Otherwise, we cannot demonstrate it, isn't it? So, now in a load control analysis, what we do, let us say this structure is in equilibrium at this stage. Now, I apply an incremental external load, which is my R delta Ren. Okay. Delta is for the increment, E is for external, and N is this load step. This much I have applied, right. So, objective is to determine the displacements of all the nodes at all DOFs in the structure. So, what we do in a Newton-Raphson iteration, if you remember, we form the tangent stiffness matrix and we divide this unbalance. Basically, we solve the equation, okay, and we get this incremental displacement in the first iteration delta R1. Okay. So, what is my total displacement? Well, this is equal to this displacement plus that displacement. So, this is my new displacement, right. at this displacement, I perform a state determination. In other words, what I do for this displacement, I go to each element, calculate the displacement in global coordinates, go to the deformation coordinates, determine the internal forces, transform back to global coordinates, assemble them, okay, and then I get this internal resisting force vector Ri at the end of second iteration, right? Now, you see from here to here, this is the load I want to apply, right? So, there is an error. So, this is the equilibrium error or the unbalanced force at the end of the second iteration. When we started this load step, then this entire thing was my unbalanced, right? So, it has reduced. Now, at this point, I again determine the new tangent stiffness matrix, okay? So, that means I am going like that, right? And then this is my new displacement. This is the new incremental displacement. So, the previous we were here plus this. So, this is my current displacement, and at this stage I have some unbalance. So, which is reduced, right? And I do again another tangent here. So, I continue doing this until my unbalanced force vector satisfies a convergence criteria which we have discussed in this particular lecture. Okay, there are few based on the norm of the unbalanced force vector, based on the norm of the incremental displacement, based on energy, and so on. Okay. Now, if you do a modified Newton-Raphson iteration, then what we do, at the first step we form this tangent, and in the subsequent step we do not form the tangent. So, we go parallel to this, okay. So, then we come here again go parallel to this, and if you go back, you will see that modified Newton-Raphson takes more number of iteration to reach the converge solution, okay. So, whatever I stated is briefly written here, and I am not going to go through because I have already gone through it once in lecture number 13, okay. Here I want to mention that this capital K, which is the tangent stiffness matrix in the jth iteration, can be constant. That means you calculate at the beginning of the load step and keep it constant during the iteration. So, that is modified Newton-Raphson, and when it is tangent you form it at every iteration, then it is Newton-Raphson. And also this can include the geometric stiffness matrix. Also, the internal resisting force vector that we are calculating, now we know how to handle geometric nonlinearity, okay. So, this Ri can include the second order forces, that means the P delta forces that you are calculating, okay. So, these are the 2 points I wanted to note, right. So, this is a load control analysis, that means I apply certain load and I iterate to achieve my or determine my equilibrium condition. That means when the external force is in equilibrium with the internal force, and then this is my displacement, okay. Now, let us consider that as we have a structure, the response of which is going like that, right. That means every system will show this kind of behavior. Force deformation is initially linear, then it becomes nonlinear, and then eventually reaches the peak value. Depending on how much ductility the system or component has, you will get a flat behavior, and eventually it will drop, right. So, that is what I am trying to show you here. Now, when you are doing a load control analysis, so what you are doing? You are actually increasing or applying load in small steps, and in each step you are solving a linearized problem, right. If I go back in each step, so within this from here to here, from this to this, you have applied this, and in each step you are solving a linearized problem, iterating and achieving this solution, isn't it? So, let us say we keep on applying this small load increment, okay, and when I go up to this point, no problem, I can do Newton-Raphson or modified Newton-Raphson iteration, determine the internal forces, and the structure will be in equilibrium, no problem, right. Now, after this point, or let us say you also apply another increment which corresponds to that, the peak value, okay. After this point, if you apply more load, if you apply another increment, what will happen? Well, in a numerical setting, in a computer program, the solution will never converge because the structure has no strength above this point. So, if you apply more load, if your load is here, right, and the structural strength maximum is here, so that difference can never be met. That means the equilibrium can never be achieved. There will not be any convergence of the solution. Now, in reality, if you do this, reality in the sense, in a laboratory setting, let's say you have a structural component, and typically we use hydraulic actuators, okay, to study the force deformation behavior of structural components and systems. So, let's say you take a hydraulic actuator and you're pushing a component, right, and you are applying load. Okay. So, let us say this component behavior is something like this. So, when you are applying or increasing the load through the actuator up to this point, no problem. But after that, if you ask your controller to increase the load, okay, what will happen? The actuator will keep pushing the specimen because it is trying to achieve that load. But the element, the structural component which is offering resistance can never give that resistance because its strength is only this much. So, what will happen? The actuator will keep pushing the component of the system and eventually bring it down to collapse. Okay? So, the point I am trying to make, so there will be sudden collapse. Okay? The point I am trying to make, just like in a numerical setting or a computer analysis, there won't be any convergence. In reality also, if you do a load control analysis, after this point, you will not get this behavior. Okay? So, that is the limitation of a load control analysis, right? If you say, well, after this point, the force is reducing. What if after going to this point, I start to reduce the load? What will happen? Will the structure go like that? No, it cannot. So, at this point, if you start to reduce the load, what will happen? The structure will unload elastically, right? Where this stiffness is going to be about the same as the initial stiffness, depending on how much deterioration is happening in the structure. But typically, this and this will have very similar stiffness, right? So, this part, the post-peak response cannot be captured using a load controlled analysis. Okay? So, that is what I say here, no convergence after it reaches the peak strength. In reality, structure will collapse when pushed with load greater than its strength. That is obvious, isn't it? So, the question is, how do we get this post-peak behavior? Because often we are interested in the post-peak behavior. Okay? So, especially in earthquake resistant design. So, how do we get this post-peak response? Okay? So, that is where we have to do displacement control analysis. Now, throughout this course, you have done displacement control analysis many times in OpenSeas, okay, and we have not discussed the theory. So, now we will understand what is the theory behind a displacement control analysis. Okay. So, before I get into displacement control analysis, again let us take reference of this same example that we studied in the previous lecture, that is lecture number 52. Okay. So, we have done a large displacement analysis of this and determined the force versus displacement relationship, assuming linear elastic material behavior. Okay. So, this was the deform configuration. Now, I will directly go to the result. So, what did we do? This green is the response that we got, okay, when the structure goes from the configuration A to configuration F, and I have discussed all this point A, B, C, D, E, F, right. And I have also shown you the same example in OpenSeas. Feel free to go ahead and look at it, and you will see that I have done a displacement controlled analysis. Okay. That means I kept on increasing this displacement, and then this is the force versus displacement response I obtained, right. Now, the question is, what happens if I do a load control analysis with this system, right. Let us first talk about it in reality. So, you have this kind of an arch with two members, right, and you keep on increasing load. So what will happen? The structure will start to take more and more load, more and more load. So you will go along this path, right, up to the point that is called the limit point, right? So if you keep increasing, put little bit more load, what will happen? Well, beyond this, it cannot go. If I do a displacement control analysis, it is going in the other direction, but I have increased the load. So what will happen? This has to go all the way to the right like so. Okay, so this will completely snap to this point, and then again it will start to take more and more load. So it will go along this path. Okay, what is this point? Well, let me name it B prime. Okay, where is this B prime? Well, it is between E and F. The configuration is going to be something like this. Okay, so this is my configuration B prime. So that means if you do a load control test with this, you keep on increasing this load, you'll get configuration B, and after that it will snap to configuration B prime, which is this. The intermediate events cannot be captured if you do a load control test, right? And this is going to be a dynamic event, which probably you can imagine. Okay. On the other hand, if I do the same thing in a computer program, try to analyze the structure using a load control technique, then I will show you that actually you will be getting this response, which is called snap through behavior. It is snapping through from this configuration to that configuration. Okay. So here is the example that is done in OpenSeas. Let me quickly show you that. So as far as the modeling is concerned, I am using co-rotational truss element, same as before, because we are doing a large displacement analysis. Okay. So first what I have done the analytical solution and determine what is the maximum load that I am applying corresponding to this 2.5 times the height, that is the displacement I am going to go through. Okay. So P max, that is stored here, right, and then I created the model. Okay. So here is the model, right, and then what I am doing, I am applying at node 2 in the negative y direction, vertically downward direction, this force P max using a time series which is linear. That means I will be increasing the load starting from 0. Okay. Here is the analysis configuration. I am doing load control. Okay. In the previous example, that was displacement control. I am doing a load control. In how many steps I am applying the load? I am applying the load in n steps. So this is called a factor lambda, which is 1 divided by n steps. That means at each step I am applying a load P max multiplied by 1 divided by n steps. This much load I am applying in each step. Okay. And then performing the load control analysis, and then I am storing the displacement of this node 2, the middle node, in the vertical direction, and in the other column of this data matrix I am taking the load factor. Get the load factor multiplied by P max is my load. Or you can calculate the reaction, vertical reaction of node 1 and 3, you will get the same answer. Okay. Or you can do P max times J divided by n steps, that will also give you the same answer. So let us say I am doing the load factor, and then I am plotting the response. So these are all to denote those A, B, C, D. So here is the result. OpenSeas co-rotational using load control. What you see, it goes like that. And then the green is the analytical solution using large displacement, which is done purely analytically. And that we have already compared when we do displacement control, then it follows the green. Okay. So this is called a snap through phenomena. Okay. So what we want to now discuss is how do we do displacement control. So if I go back to this problem, if we do a displacement control analysis, that means right from here, point A, if I keep on increasing the displacement, I am basically going to the right. I am slowly imposing the displacement and measuring the resistance, then I will be following this path. I will be capturing this behavior completely. Okay. The question is, how do we perform the displacement controlled analysis? In OpenSys, you already know how to do the displacement control analysis. But what is the theory behind it? Let me try to explain that. Okay. So let's say we are talking about the force versus displacement. Okay. Let it be a single degree of freedom system for the time being. And let's say this is the force versus displacement. So what is the idea? Well, I'll be applying small incremental displacement, and I'll be determining the state of the system. So that is the state determination. So that is my external load. Very simple. It is trivial, right? Yes, it is trivial for 1 degree of freedom problem, because for a single degree of freedom problem, you apply the displacement, apply another displacement, determine the state which is in equilibrium with the external force. So you apply displacement, you know the load. That is exactly what I did in the previous example. That was a single degree of freedom problem. Okay, I can easily do a displacement control analysis. And as the displacement keeps increasing, you can capture this entire behavior, the post peak behavior, without any problem. Okay. So for a 1 DOF problem or a single degree of freedom problem, let me show you what it means. So let's say I take a cantilever element, cantilever column like this, which is fixed here, and here I am restraining the rotation by putting a guided roller, and in the vertical direction also it is restrained. So there is only 1 degree of freedom, little r and capital R. So little r is my displacement, capital R is my corresponding force, right? So if I apply some displacement little r, then this will deform like so, right? So how much is the force required to cause this deformation? Well, corresponding to this little r that I have applied, what I have to do? I have to calculate my basic deformations, right? What are the basic deformation? For a nonlinear beam column elements in the basic or deformation coordinate system. So these are my degrees of freedom, theta I, theta j and delta. Okay, we call this is V1, this is V2 and this is V3. So calculate this deformation from little r, okay, and then determine the corresponding S, the moment here Mi, Mj and this one, okay, and then you can calculate the r, because it's a single degree of freedom system. So basically it reduces to a state determination. There is nothing else involved in this. Okay. Alternatively, I can show this for a single degree of freedom system. Let's say this is my r and this is little r. Okay. This is the actual behavior of the system. Okay. So what we can do, we can apply some arbitrary external force. Let's say my structure is in equilibrium at this displacement and this internal force. Okay. Then I am applying some arbitrary incremental external force. Okay. So using the tangent stiffness, I can predict how much is my displacement, right, corresponding to that load. But I don't want to apply this much displacement. I wanted to apply displacement here. So what I can do, I can take this and scale it back. I can scale back to delta required, right, and then I can determine what is my internal resisting force vector, right. Looks so simple, isn't it? So this is through state determination, and then external force is equal to the internal force. But this works only when you have a single degree of freedom system, or if you have a linear elastic system. If you have a linear elastic system, this is behavior is linear. Okay, you take a linear elastic system, apply some load, you get a displacement at a point. Now if you want to determine what should be the load when the displacement is some other value, you just calculate a scale factor and multiply by the load, right? That is what I am trying to tell you. If the behavior is linear like this, then this is fine. Or if it is a single degree of freedom system and nonlinear, then this is fine. For multi-degree of freedom system, this cannot be used. Why? Because my external force vector Re and the internal resisting force vector Ri are generally not parallel. So, when two vectors are not parallel, or when they are parallel, that means one is a scalar multiple of the other, and we are talking about n-dimensional vector, right? So, typically they are not parallel until convergence is achieved. That means until Re is equal to Ri, and at that point they are actually pretty much equal, within some tolerance. Okay. So therefore, this procedure cannot be used. Okay. So what do we do then? Okay. Let's try to understand the basics, and in the next lecture we'll continue with this. So let's say we have a multi-degree of freedom problem and consider the structure is in equilibrium at the nth load step. Okay. So in other words, let's say this is for MD wave and the structure is in equilibrium at this point. So that means at this point Re n is equal to Rin. Okay. Now I am trying to write down the linearized equations of equilibrium for the n plus 1th load step, and I am still applying external incremental load. So let's say I want to apply this much load. So I can write my tangent stiffness multiplied by incremental displacement vector is equal to this incremental external force vector plus this unbalanced from the previous step. Now this step is an equilibrium step. Okay. In principle, they are equal, but in a nonlinear analysis, this will never be identical. There will be some acceptable small difference, right? So whatever be that acceptable small difference, we typically carry it. So this minus that is this unbalance, right? This is the equation that I am writing for this step. Okay. Now all the terms are explained. Kn is the initial or tangent stiffness. Okay. This is the incremental external load vector. This is external force at the nth step, internal resisting force vector at the nth step, and this is the unbalanced force at the nth step, right? What is the objective? I want to control a single displacement. Let me give you an example. Let's say I have a multi-story building, right? Like so. And I am trying to push this building from left to right using some load. Okay. Now I could be applying some load here, some load here, some load here, load here, right? And remember, if I apply load incrementally, increase all the loads proportionately, okay, using some profile, I will not be getting the post peak response. So I have to control the displacement. Now let's say I am controlling the horizontal displacement of this node, right? When this has certain profile, and I will keep multiplying this load pattern by certain number to achieve a particular value of this displacement. In other words, I want, let's say, this displacement to be 5 mm. What is my force required here? Then I want this displacement to be 10 mm. That means I am applying another 5 mm, then 15 mm, and so on. What are the corresponding forces maintaining that same pattern? Okay, that is what we are trying to determine, right? So that means we choose a single displacement, okay, to be my controlling displacement. So in that controlling degree of freedom, I will specify an incremental displacement which I am calling delta for increment, and then R for displacement, putting a hat to indicate that is my known displacement which I want to achieve. Okay. This equation is linearized. What is the equilibrium equation that we have to satisfy? Well, we have to satisfy the unbalanced force vector at the n plus 1th load step, which is the external minus the internal. Now, internal is a function of Rn, that is the previous displacement, plus the incremental displacement. This must be equal to 0. And always remember that this is a complicated or complex nonlinear function of this displacement, right? Now, what is our known displacement? If I write let us say this delta Rn is a vector. What is the size? Well, if we have n degrees of freedom, this is n cross 1. And in this, I have many entries. And in this, one of the entry is known to me. So, this increment is known. At that, let us say roof displacement, I want to go 5 millimeter, right. So, this is known to me. The remaining are unknown. Okay. So, this delta R hat is contained here. Now, how do I satisfy this equations of equilibrium? It is not easy. We have to develop an iterative procedure to satisfy the equilibrium here, okay, so that at a particular degree of freedom, I get that displacement, right. How do we do that? That we will discuss in the next lecture. But before we conclude, remember that at a given degree of freedom, okay, let me go to this example. So, at each node, let us say this is a planar frame, I have got 3 degrees of freedom, translation in the x, translation in the y, and rotation. Now, at any degree of freedom, we must be knowing either the resisting force or the displacement. The two cannot be known together before we solve the problem. Okay. So, one is known. So, when I am saying I want to go to 5 mm here, or I want this horizontal displacement to be 5 mm, so I know that displacement, but I do not know what is the corresponding force required. In other words, if I take a simple problem, okay, let us say I take a cantilever, right. So, at this I have got R1, R2 and R3. There are 3 degrees of freedom, right. And I am saying that this is the load I want to apply, okay. And this is going to deflect like that, and let us say there is a plastic hinge that is going to form here. So, I want to control this displacement little r2, okay, by changing that, right. So, that means this is my unknown, okay. What about R3? Is it known? No, it is not. But I know the force in this degree of freedom is 0. R3 is, the displacement is not known, but the corresponding force is known. Similarly, R1, the displacement is not known, but the corresponding force is 0. Nothing is applied. I only applied that one. Okay. Now, for this particular case, R2, my displacement is known, but R superscript E is not known. Okay. With that in mind, let us continue in the next lecture, and we will derive, or we will go through the procedure how to solve a problem using displacement controlled technique. So, with that, let me summarize. In this lecture, we have talked about the limitation of load control analysis, okay, that when you do a load control analysis, beyond the peak, you cannot get any response, okay. Post peak response cannot be obtained using a load control technique. And then I have introduced you to the concept of displacement control analysis. In the next lecture, we will discuss about the displacement control analysis, and we shall also discuss the limitations of displacement control analysis, and there the other methods such as arc length method will come into picture. Okay. So, with that, this is one reference that I have used in this lecture. We will use it more in the next lecture. Okay. So, with that, thank you and see you in the next lecture.